Hi students, in the last class we discussed about a single sideband suppressed carrier derivation and power saving. So with respect to power saving of DSB-SC system, the power saving equation becomes PT dash minus PT double dash divided by PT dash into 100. So while we substitute all these values from the previous derivations, we will get a square PC by 2 minus MA square PC by 4 divided by MA square PC by 2 into 100. So the first term, which represents double sideband suppressed carrier total transmitted power, and the second term, which represents the single sideband suppressed carrier total power. So with respect to DSB-SC system, while considering MA is equal to 1, this equates to 50%. So 50% of power is saved when compared with DSB-SC system. So by combining all these comparisons, when compared with AM or DSB-FC, the percentage is improvised 86.3, whereas with compared with the DSB-SC, the percentage of efficiency is improvised up to 50%. Then applications of SSB. It is used to save applications where such as power saving, like a mobile system in which weight and power consumption must naturally be kept low. So there we can use SSB. Single sideband modulation is at premium. Point-to-point communication, air, mobile communication, TV, telemetry, military and radio navigations, we can use this SSB. Advantages: power conservation, bandwidth conservation, selective fading and noise reduction. So these are all the advantages of SSB. And disadvantages: complex receivers while compared with the DSB-SC and DSB-FC. Here we need to produce coherent reduction or synchronization circuit. Then tuning difficulties. This is quite complex and expensive tuning circuits are required. So this is what SSB. Then how to generate SSB. So the SSB can be generated by 3 different methods. One is filter method, or we can call it as frequency discrimination method. The second method is frequency discrimination method. Under frequency discrimination method, we have 2 types. One is phase shift method, another one is modified phase shift method. First we will discuss about frequency discrimination. So from the name itself, it is a frequency discrimination. So the unwanted frequency or the upper sideband or lower sideband frequencies are eliminated in such a way that we are using selection filters. Either we can eliminate the unwanted frequencies by using the filter, or we can choose or opt the desired frequencies with the help of this suppressing filter. So this is a block diagram: crystal oscillator, buffer, balanced modulator, and here we are giving our input signal AFN, audio amplifier. So this is called as frequency discrimination filter, and here it is the outcome, balanced modulator output. So in this method of SSB generation, the balanced modulator, after this balanced modulator, the unwanted sidebands is removed with help of the filter, either upper sideband or lower sideband. By choosing the required frequencies, we can opt either the upper half or lower half. So in carrier frequency, another requirement, such a filter must have a flat band pass and extremely high attenuation outside the pass band. So in the radio communication system, the frequency range used for voice is 300 Hz to about 2800 Hz. It is in almost cases. If it is required to suppress the lower sideband and it is transmitting frequency is FC, then the lowest frequency, that is, this filter must pass without attenuation, is plus 300 Hz, whereas highest frequency that must be fully attenuated is FC minus 300. So we need a filter whose transition band is very low. This situation becomes worse if the lower modulating frequencies are employed, such as the 50 Hz minimum in AM broadcasting. In order to obtain the filter response curve with skirts as steep the quality of the tuned circuit must be very high. The initial modulation takes place in the balanced modulator at low frequency because of the difficulty of making adequate filter at high frequencies. The filter is a bandpass filter with a sharp cutoff frequency at either side of the bandpass to obtain the satisfactory adjacent sideband rejection. The filtered signal is converted in a mixer to the final transmitter frequency and then amplified before being coupled to the antenna. The integrated ceramic filters are used, such as sideband filters. The drawback of this filter method is it requires a sharp filtering, which requires filters with high tuning. Primary modulation cannot be done at the transmitting frequency, which is another drawback of the filter method. So we are moving to phase shift method. So what are all the drawbacks we faced in the frequency discrimination method? It is overcome in your phase shift method. So the phase shift method is the same as generation of SSB. That is, we use this same block diagram for derive the SSB equation. Modulating signal is given directly to one balanced modulator, and the signal is phase shifted, and again it is given to balanced modulator 2. Similarly, in the carrier also phase shift is introduced. So with the help of this summer, we can able to eliminate the unwanted sideband frequencies. So this is the basic principle of phase shift method. That is, we are introducing phase shift while transmission at the modulating signal as well as carrier signal. So this is the equation, the same equation. So EM sin omega EMT is the modulating signal. Here we are introducing 90-degree phase shift, so it becomes cos omega CT. Similarly, in the balanced modulator 2, we are introducing 90-degree phase shift, so it becomes cos omega MT. Then we need to multiply this, sum these two equations. We will get this V0 is equal to V1 plus V2. So EC EM sin omega C plus omega EMT. The negative sideband get cancelled. So one of the sideband is cancelled, whereas the other is reinforced. This method avoids the use of filters. So the balanced modulator and the phase shift itself avoid the unwanted sideband frequency. Then modified phase shift method. So it is the advanced method of phase shift method. Again, here we are introducing phase shift in two ways. That is, input signal is directly given to balanced modulator, and the input signal is phase shifted. Again, it is given to balanced modulator 2. Then local oscillator frequency is also phase shifted and given back to the BM4 and directly given to BM3. So the operation is input signal is directly passed through the low pass filter, and again it is directly given to another balanced modulator. At the same time, the second half, this is here the input signal is 90-degree phase shifted, carrier is also phase shifted, then it is given to low pass filter, then it reaches BM4. Here also the phase shift is introduced, and finally we can sum all these things, so the unwanted sideband frequency can be eliminated. So the Weaver's method, the modulators 1 and 2 both have the unshifted modulating signal as inputs. So BM1 takes low frequency subcarrier with 90-degree phase shift from the AF oscillator. BM2 receives the subcarrier signal directly from the oscillator. This method tries to avoid the phase shift of audio frequencies and combine the audio frequency carrier with AF, which lies in middle of audio frequency. The low pass filter at the output of BM1 and BM2 with cutoff frequency ensures the input to the balanced modulator BM3 and BM4. The output of BM3 and BM4 gives the desired sideband suppression. The next one is mathematical analysis. The modulating signal is given, and AF subcarrier signal is also given. Here we are introducing phase shift in the modulating signal as well as the carrier signal. So BM1, this is the modulating signal, it is the phase shifted modulating signal. Similarly, BM2 modulating signal, and carrier is also phase shifted. So the output of the low pass one is E3 and the output of low pass 2 is E4. While combining these two, we can get the final outcome. So assume EM is equal to E out, that is output voltage, this is equal to 1, then E5 is equal to 2 cos omega naught t plus 90 degree minus omega mt into sin omega ct. So the input for balanced modulator BM4 is written as like this. So while combining BM4 and BM3, we will get the output equation as 2 sin omega naught omega c minus omega m plus 90 degree. The other two terms cancel with each other because it is out of phase. So we can get 2 into cos omega naught plus omega c minus omega m into t. The final output frequency is omega naught plus omega c minus omega m, which is essentially the lower side band of RF carrier omega c plus omega c. Thank you.